Hello, welcome to my talk on Bernoullis principle and Bernoullis equation. In this talk, we will see how our pioneer fluid dynamicists managed to solve this fluid dynamic problem step by step. In modern fluid dynamics, Bernoullis equation might be the most used equation for both engineering applications and in research. In this talk, we will see how the Bernoullis equations can be derived for different flows, from the simple one-dimensional flows, such as the flows in pipes, to the more general Inviscid flows derived from Euler equation, and to the complicated unsteady potential flows. And we will also see, in applying these Bernoullis equations, some assumptions must be applied. For instance, Bernoullis equation is only correct for Inviscid flows. Although those limits the practical applications of Bernoullis equation is very wide in fluid dynamics, which makes the Bernoullis equation the most applied equation in fluid dynamics. This can be seen in my talks about the applications of Bernoullis equations in future. Let's first have a look at the understandings to fluid dynamics before Bernoullis. Aristotle, in about 350 BC, he described the fluid as a continuum and suggested that the body moving through a continuum would encounter resistance. Archimedes, in 250 BC, he proposed the law of buoyancy. A body immersed in a fluid experienced buoyant force equal to the weight of the fluid it displaces. And he also initialized the understanding of fluid pressure. In fluids, each part is always pressed by the whole weight of the column perpendicularly above it. In about 1500, Da Vinci noticed the law of continuity, that is, the mass conservation, and he also stated the resistance is directly proportional to the area of the body. And Galileo was the first to formulate the fluid resistance, which varies proportionally to the density of the fluid. And he tried to build the relation of the fluid velocity and the fluid resistance. But he wrongly concluded that the resistance is proportional to the velocity. In the modern understanding, the resistance is proportional to the velocity squared. There were three famous experiments for understanding pressure and atmospheric pressure, including Torricelli's vacuum experiment in 1643. He could measure the atmospheric pressure and create a vacuum. And the barrel burst test by Pascal in 1646. He created the pressure in a long vertical tube. Large pressure caused the barrel burst. And he also proposed the Pascal's principle, which is widely used for engineering applications, such as we see use the Pascal's principle to lift a car slowly and easily. And in 1656, in Marburg, the hemispheres experiment, the two hemispheres put together and the air inside was taken to make a vacuum in the hemisphere. In the experiment, 16 horses used, 8 on each side, to try to pull a part of the hemispheres, but it not separated. Based on the calculation, there was 20,000 newtons force acting on the hemisphere. And in 1687, Newton published his book, Mathematical Principles of Natural Philosophy, in which the famous Newton's second law of motion provide a fundamental equation for fluid dynamics. Euler established the fluid dynamic equation, namely Euler equation, which is the foundation for the complete fluid dynamic equation, Navier-Stokes equation. And Newton also defined the viscous stress for the fluid, the Newton's law of viscosity. Here, this is the principle for defining the viscous stress. Newton was also the first to theoretically verify the fluid jerk is proportional to the velocity squared. And only Peter invented Peter tube in 1733, which is a simple device used for measuring fluid speed. Today, Peter tube is still widely used in engineering in the measurement of the fluid speed. However, we must note this invention was before Bernoullis principle, which was published in 1738, and the Bernoullis equation, derived by Euler in 1752. So we can see, before Bernoullis, the Bernoullis' father, Johann, and the son, Daniel, the important relation between fluid velocity and the pressure has not established. But this relation is the fundamental relation for the fluid dynamics. Here comes the Bernoullis' father and son. Daniel Bernoulli, the son of the Bernoullis, published his book Hydrodynamica in 1738, in which he initialized the pressure-velocity relation, named Bernoullis principle. Pressure decreases when the fluid speed increases. He also drew a picture in his book as this. However, if we use this drawing, the Bernoullis principle can be more easily to be understood. Here we use two different pipes for the fluid. In here, the large pipe means a smaller velocity, so the pressure here would be smaller than here, where the fluid velocity is very small or zero. And for the smaller pipe, the velocity V2 is higher than V1, and the corresponding pressure in this small pipe would be smaller, so H2 is lower than H1. It should be noted both Bernoullis had attempts to solve the problem, many based on the energy conservation, while a more general solution for the unsteady quasi-one-dimensional flow was derived by the father, Johann Bernoulli, in his book Hydrodynamica, published in 1743. See the reference given in here. Next, we will see how the Bernoullis equations can be derived for different flows based on different principles. The first derivation is the simplest, and the physical meaning can be very straightforward. This is derived from the Newton's second law of motion, which can be regarded as energy conservation among the mechanical energy, including kinetic energy and the potential energy. For the one-dimensional flows, such as the flows in a pipe, or simply in a theoretical steam tube, see this picture. And we can take a segment of the pipe or the steam tube. See this delta S. At the one end of the position S, the section area would be A, pressure P, and the velocity V. And at the position S plus delta S, here the section area can be taken as A plus delta A, and the pressure is given as P plus delta P, and the velocity V plus delta V here. So the first, we calculate the force acting on the segment on the S direction. F is given as this. Here, this part is the surface force due to the pressure, and the first two terms are the force acting on both ends, here and here. And the third term is the pressure acting on the surface due to the different section area, A and A plus delta A. So this part due to the pressure for the difference of the section area. And this part is the body force, the fluid gravitational force. By dropping the higher order terms, we can have the expression for F given by this. Here, rho is the fluid density. For incompressible flow, it is a constant. Now we can apply the Newton's second law of motion, the momentum equation. The dynamic equation is given as this. The left-hand side is the force F, and the right-hand side is m, the mass of the segment. And this part is the acceleration of the fluid in the segment. So we remove delta S, we have the expression given by this equation. Now here, the acceleration can be expressed in this form. So we put this together, we have the expression given as this. And this, consider the sine alpha times ds is actually the increment on z direction, given as dz. So this equation can be written as this, and this equation can be integrated, given as this. So here, C0 is the integration constant, and this is the Bernoullis equation based on the energy conservation. And we can see from the derivation here to here, if the fluid density rho and the fluid gravitational acceleration g are both constant, we can obtain this integral form of the equation. For instance, if the fluid is compressible, the density rho is not constant anymore, then we cannot integrate this equation into this equation. This means this Bernoullis equation is valid for incompressible flow. And also, we must note, in deriving this Bernoullis equation, the fluid viscous stress is ignored. So, this Bernoullis equation is only valid for inviscid flows. The second derivation for the Bernoullis equation is based on Euler equation. In modern fluid dynamics, Bernoullis equation is generally regarded as the integral form of Euler equation. In the history, Euler derived both Bernoullis equation and Euler equation in an order of Bernoullis equation first in 1752 and then Euler equation in 1757. However, here, in deriving the general Bernoullis equation for inviscid flow, Euler equation is used to derive the Bernoullis equation here in the talk. For an incompressible inviscid flow, the fluid dynamic equation is given as Euler equation as this form. Here we can see the fluid acceleration in the bracket, and the fluid body force is given as the vector F, and the surface force due to the pressure given in this. To derive the general Bernoullis equation, the flow is considered as a steady flow. So, the Euler equation is reduced to equation as this. And for the Bernoullis equation, the body force must be conservative force. Here, only the fluid gravitational force is included for the analysis. Here, in Cartesian coordinates, where the z-axis is positive, pointing up. Therefore, the body force, the vector F, is given as this and can be expressed as the gradient of this function. In the derivation, there is one difficulty term for the acceleration, the convective acceleration, but we can employ the vector calculus identity here. So if we take the vector A and B same as the velocity vector v, then the vector calculus identity can be expressed as in this form. So we can calculate the convective acceleration, this term, given by this expression. And we change the order of the cross multiplication for the vector, so we have the expression as this. As such, the Euler equation can be written in a form as this. Now we consider a special case on a fluid streamline. So the equation would be given by this differentiation form. And based on the definition of the streamline, we can see on the streamlines, the vector ds has the same direction as v. Therefore, the core of the velocity vector cross timing the velocity vector would be perpendicular to the velocity vector v, since if we take the core of the velocity vector as an vector. So we can see in this equation, the last term on the left-hand side would be 0 because the vector ds is same as the vector, but this term would be perpendicular to the velocity vector. Therefore, the dot product of these two terms would be 0. And then the equation can be expressed as this. Here, we must note the density ρ and the gravitational acceleration g are both constant. Otherwise, we can't obtain the relation as this. And obviously, we can integrate this equation and obtain the relation as this. Here, C1 is the integral constant, which can be decided for different situations. So in here, we can see for the general Bernoullis equation, the fluid must be inviscid, incompressible, and the body force must be conservative, and the Bernoullis equation is valid only on the same streamline. Now we look at the example for the Bernoullis principle. So based on the Bernoullis equation here, and if we take the tank bottom as the reference, so this term would be constant. And we can combine this constant and the integral constant. So we have the expression as this. Here, C2 is another constant. Based on this equation, we can understand the Bernoullis principle. The pressure decreases when the velocity increases, such that these two terms together make a constant C2. Now we can explain this drawing. In the tank, the velocity here would be 0 or very small. Therefore, the corresponding pressure P0 is high, so we can see the fluid level H0. The large pipe for P1, since the fluid velocity V1 is larger than V0, therefore P1 would be smaller than P0. That means H1 is lower than H0. In the small pipe, where velocity V2 is larger than V1, hence the corresponding pressure P2 here would be smaller than P1. Therefore, in this experiment, P2 is lowest, meaning H2 is lowest among all three heights. So as such, the Bernoullis principle can be well explained by the Bernoullis equation. The pressure decreases when the fluid speed increases.